Variation of parameters is another method to help us solve non-homogeneous differential equations. Now, we already saw that we could do undetermined coefficients, but the drawback to that was you could only use that method if the function on the other side, the non-homogeneous part, had repetitive derivatives. So if the function on the other side doesn't have a repetitive derivative, that method won't work. So we need a more all-purpose method that works every single time, no matter what. That's going to be our variation of parameters. Now, it can be a little bit more difficult. That's why we kind of want to have a simpler method if available to us. Here's the idea behind this. If we start out with, let's just do y double prime plus p of x y prime plus q of x y is equal to some function of x. This is just our second order linear differential equation. This doesn't necessarily have constant coefficients. In this case, those could be functions of x, but this is definitely not homogeneous. Now, the non-homogeneous function part's only defined when the elite coefficient's 1. That's kind of got to remember to always divide through by that before you do this method. All right, here's the idea. We know that here we'd end up with some complementary solution, which would be some c1y1 plus c2y2. Right? We'd have two solutions to the second order differential equation to the homogeneous part. And we saw when we were doing like our undetermined coefficients that we had to check to make sure that didn't show up over here because we knew that would be part of this solution, the homogeneous solution, not to the non-homogeneous solution. So the idea from this is I know for a fact that the particular solution can't have a constant multiple of either y1 or y2. One would guess, though, it would be some function times those. So I should be able to find a function, let's say some u1 of x times y1, plus another function u2 of x times y2. So there's a pretty good reason that you would assume this because you know that y1 or y2, a constant multiple of those cannot show up in the particular solution. So generally it would have to be some function multiple. Now, we saw earlier when we did undetermined coefficients, our function was x when it repeated, but there's no reason to assume that it's only an x. So if we're going to assume that this is our solution, we would have to take all the derivatives of this, plug it into this, and figure out what u1 and u2 were. If we can do that, then that would be our solution. So let me, this is going to be pretty messy. Let's take all the derivatives. I'm going to drop this function notation for right now. So our first derivative is going to be u1 prime y1 plus u1 y1 prime. Product rule over here is going to be u2 prime y2 plus u2 y2 prime. All right, now we'd have to find the second derivative here, and you see that's going to be pretty messy anyway. Now, we're going to cheat a little bit here. Now, there's actually some good mathematical reasons for cheating, but think about it like this. If I start taking the derivative of this first term and this third term, I'm going to have to do the product rule, and I'd end up with the second derivative of u1 and the second derivative of u2. Remember, we're trying to solve for u1 and u2, and by taking the derivative of those things, again, I'm making a second order differential equation with two different things I'm trying to find. That's really, really complicated. So let's do this. Let's say let's let u1 prime y1 plus u2 prime y2 be 0. Right? Those would be these two pieces here. Since we're adding them up, let's say when you add those two things up, they're 0, which means I don't have to take the derivative of those two pieces at this stage. Again, that's really just helping us clean this up so the derivatives don't get horrible. So we're kind of saying that these two are going to add up to 0. All right, so let's take the second derivative then. So now I'm only looking at these two pieces. That's u1 prime y1 prime plus u1 y1 double prime plus, product rule here, u2 prime y2 prime, u2 y2 double prime. All right, I'm actually going to swing this down over here. Let's let u1 prime y1 plus u2 prime y2 be equal to 0. Because I need a little bit of room. Okay, so that's a condition that we've already imposed to this problem, but as long as we can still find u1 and u2, that might be a valid assumption. So we're going to take our second derivative, our first derivative, and our function, these three, and plug it in here and see what we end up with. Well, it's going to be kind of long and ugly, but let's see. We get our second derivative is u1 prime y1 prime plus u1 y1 double prime, u2 prime y2 prime, u2 y2 double prime. There's our second derivative. Plus p of x, I'm dropping the function notation, times our first derivative. Now for our first derivative, again, I can ignore these two pieces because I said that those are going to be 0. So all I end up with here is u1 y1 prime plus u2 y2 prime plus q of x times our guess, u1 y1 plus u2 y2. That's got to be equal to f of x, right? That's our differential equation. All right, I'm going to go ahead and distribute here. So one more line, u1 y1 prime, u1 y1 double prime, u2 prime y2 prime, u2 y2 double prime, pu1 y1 prime, pu2 y2 prime, qu1 y1, qu2 y2 is equal to f of x. All right, long line. All right, now since I'm looking at these u1s and u2 stuff, I'm going to group by u1 and u2 real quick. Let's take a look if I factor out a u1 out of everything that has a u1. There's a u1, there's a u1, and there's a u1. So what do I have left if I take a u1 out of those three pieces? I get y1 double prime plus p of x times y1 prime plus q times y1 plus, now I'm going to do the same thing for u2. What do I have with u2s? Well, there's a u2, there's a u2, and right there is also. So if I factor out a u2, I get y2 double prime plus py2 prime plus qy2. Okay, well that's it for the u1s and u2s. All I have is two other pieces left. So I'm going to write these over here. u1 y1 prime plus u2 prime y2 prime. Okay, so all I did was just group the two last pieces I had over there alone. Now remember what y1 and y2 are. Those are solutions to the complementary equation, which means if I plug y1 or y2 into this differential equation, it equals 0. Well, this is y1 plugged into that differential equation. This is y2 plugged into that differential equation. So all of this first stuff, all of this is 0, and we end up with the condition u1 prime y1 prime plus u2 prime y2 prime is equal to f of x. Well, what we end up with is another equation that has kind of what we're looking for, the u1s and u2s in it, because we've already decided that this equation has to be true. All right, let me go ahead and get some of this out of here. So we end up having to solve a system. So and the system that we have to solve is u1 prime y1 plus u2 prime y2 is equal to 0. u1 prime y1 prime plus u2 prime y2 prime equals to f of x. That's the system that we need to solve. Now remember, from 100 years ago where we're going, we're trying to find our particular solution, which is this. So we're really looking for u1 and u2. And remember, we've already solved the homogeneous equation, so we know what these functions are. So think about it like this. I know this looks confusing, but this is just a 2x2 system with the variable that we're trying to solve for is u1 prime and u2 prime. So it's kind of like this. If I said 2x plus 3y equals 0, 4x plus 5y equals 7, right? Our variables here are x and y, and we're trying to solve this system. Same thing here, because we're going to know what y1 and y1 prime are, what y2 and y2 prime are. So our variables here are u1 prime and u2 prime. So we should be able to solve for those. Just like for something like this, we should be able to solve for x and y. To do this, we're going to use something called Cramer's rule. Now, unfortunately, for those of you that may not have had linear algebra or haven't had any matrix type classes, you're just going to have to hit the I believe button and go with this being true. We need three different determinants, three different values to help us figure this out. And the good news is you can just memorize these, and they're pretty easy to memorize. Get all this out of here. We don't need any of that anymore. So we need three different values. We're going to find W, which is just the determinant of y1, y2, y1 prime, y2 prime. We're going to find W sub u1 prime. Now u1 is our first variable, so we're going to replace the first column with the constants, air quote constant column over there. So we're going to replace the first column with 0 and whatever f of x is, and this is going to be y2, y2 prime. And then we're going to have W sub u2 prime, which we're going to do the same thing. We're just going to replace the second column with 0 and f of x. Okay, now these are just going to be three function stuff that we end up with after we do those three determinants. Which means this is what Cramer's rule says. I can actually figure out what u sub 1 prime is. That's going to be W u sub 1 prime divided by W. U sub 2 prime is just going to be W sub u2 prime divided by W. And of course, if this was a 3 by 3 system, you would have u sub 3 prime, so on and so forth, but it just extends. So now what we'd have to do to find u sub 1, so u sub 1 will be, of course, the integral of u sub 1 prime, and u sub 2 will be the integral of u sub 2 prime. And that will be our answer. Looks pretty scary. Now remember, I derived all of this for you. When we actually do them, it won't be nearly that challenging. Still be a little challenging, but not nearly this bad. So this is what we're aiming at, finding these two values and then integrating them to get the pieces. And then our particular solution, like I put on the board a minute ago, will be u1, y1 plus u2, y2. Okay, so there's the results that we're going to use. So let's just go with this. Let's go y double prime plus 4y is equal to the cosecant of 2x. And probably in your book somewhere if I had to guess. All right, so this is a second order linear differential equation with constant coefficients. So we always know that we're going to go after the the homogeneous first because this is a non-homogeneous equation. So for the homogeneous first, we're solving y double prime plus 4y is equal to 0. Again, I'm going to skip all the way to the solution. You should be able to find this quick and easy by now. So this is cosine 2x and sine 2x. So assume the solution e to the mx, plug it in, solve. Hopefully, like I said, that part's quick by now. Now we need to go after the non-homogeneous. And actually, you know what I wrote here. For the non-homogeneous, remember we'd like to do undetermined coefficients. So does our function have repetitive derivative? Well, if you start getting the derivative of a cosecant, it just starts getting bigger and bigger and bigger, and never settles down to the same functions over and over again. So it does not have repetitive derivatives. So that method won't work. So what we need to do is we're going to do our variation of parameters. So we need to find these three different values. So for our non-homogeneous, we're going to have to do variation of parameters. Now for our variation of parameters here are our two solutions for our homogeneous, which means y1 we're just going to say is cosine 2x, y2 is the sine of 2x. All right, let's find our three values now. So we're going to find the Wronskian of these basically. So it's going to be cosine 2x, sine 2x. And as you see the next row, that's our two functions. Our next one's just going to be the derivative of this, exactly like the Wronskian. That's why we're using W. So it's going to be negative 2 sine 2x and 2 cosine 2x. So that's 2 cosine squared 2x minus plus 2 sine squared 2x. Well, that's just 2, right? Factor out the 2 and you get sine squared plus cosine squared. All right, w sub u1 prime, we're going to replace the first column with 0 and the function. Now remember, it's only that function which you divided through by the lead coefficient. So our lead coefficient is a 1 here, so our function is going to be the cosecant of 2x. So this is 0 cosecant 2x, sine 2x into cosine 2x. All right, so multiply down the main diagonal, that's 0, minus multiply down the off diagonal. Well, remember, cosecant's really 1 over sine, so that's just negative 1. W sub u2 prime is going to be, let's see, cosine 2x, negative 2 sine 2x, and then we're going to replace this with 0 and cosecant 2x. Multiplied down the main diagonal, that gives us what? Cosine over sine 2x, so cosine over sine would be cotangent 2x, minus, well, 0. Okay, so there are the 3 different determinants that we need. So we're actually fairly close to the answer now. So u1 prime will be w sub u1 prime divided by w. So w sub u1 prime was negative 1 divided by w, which was, well, 2. u2 prime is going to be w sub u2 prime divided by w, which, let's see, w sub u2 prime was the cotangent of 2x divided by w, which is 2. All right, so far, other than maybe a few little derivatives, mainly algebra, pretty straightforward. So here's where this step generally gets difficult. Now we have to integrate these to get to the pieces that we need. So u1 will be the integral of negative 1/2 dx. u2 will be the integral of 1/2 cotangent 2x. All right, let's get this out of here. All right, we're getting close. So, easy enough, u1 is negative 1/2x. u2 is going to be, well, the integral of cotangent, you should know that off the top of your head. If not, u is a u substitution. Remember, that's cosine over sine. So you let the bottom be u, the top's be u, so you get the log. So you're going to get 1/4, because we get another 2. Natural log, absolute value of the sine of x. Okay, so there's the 2 pieces we needed. So remember, our particular solution is u1y1 plus u2y2. So our particular solution for this problem is negative 1/2 x. We said y1 was cosine 2x. 2x. Plus u2 is this mess. 1/4 log absolute value of sine. Hey, look, I made a mistake. Sine 2x. Times y2 we said was, well, sine 2x. Okay, so there's our particular solution. So we can now finish up this problem completely, and I'm just going to go ahead and drop right here. So our entire solution for this is c1 cosine 2x, c2 sine 2x minus 1/2 x cosine 2x plus 1/4, I'm going to write this as sine 2x log absolute value sine 2x. All right, so after all that, there's our complete solution. Now we do still have 2 arbitrary constants in here, c1 and c2. So now if you were given initial conditions, now's when you would apply these. All right, the good news about variation of parameters, it always works. So if you want this to be your fallback position, just keep practicing this method. It's fairly easy to do. The only problem that you're going to run into is sometimes the integration here is very, very difficult, and it might actually be quicker and easier to do something like undetermined coefficients. So it's very nice to have these 2 methods to help you through the problems.